Hey, hi everyone. My name is Kunal Gautam. I work as a principal architect for one of the bank companies, have worked across 20 plus countries with 50 plus customers, and have spoken at multiple Hadoop conferences. In today's session, we would be going ahead and taking a deep dive into the attention is all you need paradigm, which forms the crux of the transformers, which has been manifested as OpenAI, DeepSeek, and other large language models. So 15 years ago, when big data solutions came, there was so much of fuss around it. But if you go to the crux of it, there are only two operations that's going on there. One is file, reads and writes and append. And the second thing is external sorting. What I mean by that is you take two sorted arrays and you try to merge that. That's the whole basis of it. So in this session, we will try to delve into what's the crux of LLMs, how are they able to generate the next token, and the maths behind that. Just keep in mind, computer in itself is a binary system. What it means is it can just understand 0 and 1, and secondly, it can just do mathematical operator. What I mean by that is you can add two numbers, you can subtract, division, modulo, relationship operators like less than equal to, greater than equal to, blah blah blah. But computers don't understand language at all. So the language that we humans are speaking is quite evolved, quite complex, and computers have no understanding. So it means that that language has been abstracted out as a certain mathematical model, and the computer is just working on that model. Like the computer is somehow trying to figure out how that model will behave at a certain condition. And the behavior of that you see as an output of your LLMs, and you get the fancy capabilities of summarization, fancy capabilities of reasoning. But just keep in mind, computers have no understanding of either a character or a word or the human language. So let's begin with this fascinating ideas of how the language has been mapped to something known as vectors in computer. And vectors form the mathematical model for all the LLMs available across the world at the moment. Let's begin with some of the basic concept that in mathematics, we have something known as the line, point and line. So what I mean by that is, if you look at this diagram, you have your x-axis, y-axis, and z-axis. They are all perpendicular to each other. In mathematics, the point, it's represented as 2, comma 3, comma 4. While a vector is represented as this square bracket 2, 3, 4. What is the difference? The difference is 2, 3, 4 is just a point in a three-dimensional space. While 2, 3, 4 in the square bracket means it's a line originating from 0, 0, 0 and pointing to 2, comma 3, comma 4. So if I give you a number, example 2, what all operations you can do on top of it? So for a number like 2, you can do a division, multiplication, subtraction, addition, modulo. But in case of a vector, there are only two possibilities, or let's say there are only two base operations possible. One is scaling and other is addition. And because you do an addition, your vectors can undergo a rotation, a simple nudge, or a flip altogether. So let me show you what it exactly means. So if you have a vector, if you want to scale your vector, so the only possibility is you can either scale out the vector or you can squeeze in the vector. And it happens across the same line, right? Similarly, if you want to rotate the vector, the only possibility is you are just moving the vector in this 3D space. I also want to emphasize on the point, just keep in mind, this is a 3D space, but mathematics and the fourth dimensional or the fifth dimensional, although the human brain cannot perceive it, but in mathematics, we can say that, hey, I have a vector and it's available across 5 different dimensions. Example, 2x plus 3y plus 4z plus 8k plus 9k and 9f is a vector. It means that this specific vector is present across 6 dimensions. The vector that you see here, 2, comma 3, comma 4, it's all about 2x plus 3y plus 4z. It simply means that this is present in 3D. But just keep in mind, that this line can be present across the fourth dimension, this line can be present across fifth dimension, or nth dimension for that matter. Let's look at another interesting property, that how did you arrive here? So what did you do is, in this xyz coordinate, you had a unit vector I, j, and k. The unit vector I was represented as 1i plus 0j plus 0z. Similarly, it goes for y and z axis. So to reach to this point, what you did was you scaled out the unit vector twice. You moved, you scale the y vector by 3 times. You place the j vector as in the scale y j vector at the tip of x, and that's how you were able to reach at 2 comma 3. Similarly, from there you projected scale first of all the 4 times the j vector, and that's how you were able to get into a three-dimensional space of 2 comma 3 comma 4. So what I want you to understand is, all you are doing is traversing. That starting from one vector, you scale that, then you move ahead, then you scale something else, and finally, whatever point that you are reaching to is what you call as vectors. So vectors, again, it's comprising of only two operators: scaling, which is scale out or squeezing in, and addition. That's the only operator that you have. All right. So as I have mentioned, this vector v here, it's represented as 2y plus 3j plus 4z, right? So another interesting observation, the vectors in different domains of science is represented, or let's say is perceived differently, although they are the same. So let's look at it. So first of all, let's get into physics. So if you're talking about physics, example, if you were doing the Newtonian mechanics, where force is equal to mass equal acceleration, vectors even come there. Or if you are trying to calculate a torque, vectors are also present there. So what's the difference? The thing is, in physics, the vectors can originate at any point and end at any point. What I mean by that is, in a 3D space, it can be somewhere here. Although the center of that 3D space, 0, 0, 0, it's lying here. So physics, in vectors in physics, they do not have, it's not mandated that the starting point should be 0, comma 0, comma 0. While in mathematics, it's mandatory that the starting point of your vector is always 0, 0, 0. So that's the only difference, but it will make a hell lot of difference when we start trying to see like what is the significance of that. Similarly, in computer science, if you talk about a vector, it is either it is mostly represented as a list, or in case of a PyTorch or tensors, it is like a tensor, which is a array, very simplistically. Other part I just want you to understand is the matrix and determinants, which is again, when you study mathematics, that's a domain wherein you are dealing with how to do addition, subtraction of vectors, multiplication with a determinant with, multiplication of a matrix with a vector. Mathematical vectors have only two values. It can only be n cross m. It can never be n cross m cross z. Just take a moment, take a pause, and think about it. While in computer science, you can have an array which is of n dimensions. So that is the difference between the matrices of computer science and the matrix in mathematics. Take a moment, think about it. These are subtle differences, but makes a hell lot of difference in how you perceive it going forward. So now let's uh, delve into mathematical vectors. And as I mentioned, mathematical vectors will always start with 0, 0, 0. So let's take an example. You have a vector v1, which is pointing to 2, comma 3, comma 4, as in this specific vector. You are having a vector v2, which is 1, comma 1, comma 1. And I just want to do an addition. Just think about it. What's exactly happening? So what are you doing is, you take vector v1, at the tip of the vector 1, you place your vector 2, and wherever you are reaching is your vector v1 plus v2. Or you can do the other way around. You take the vector v2, at the tip of vector v2, you place the vector v1. Wherever is the end answer, that's your vector v1 plus v2. So all you're doing is you are taking the cumulative sum of x, the cumulative sum of y, whatever is the cumulative x and y, that's represented as the final vector. Now think about what is that I want to perceive from here. It simply means that whenever you do a vector addition, the final vector will be like the base vector will be given a nudge, and the final vector will move from its position. So either the movement can be completely inverse, the movement can be right hand side, left hand side, or somewhere in the 3D space. But the idea is vector addition will just give a nudge to the main vector so that it starts moving. Now let's move on to another important concept that hey, I have a vector v1, 2, 3, 4, and I want to change this vector from here onto a negative x-axis. Like what I mean by that is I want to rotate this vector 2, 3, 4 to minus 2, 3, 4. How can I achieve it? It means that I have to do some action, take some action, apply some function in order to rotate this vector from 2, 3, 4 to minus 2, 3, 4. So what I should be doing is, if my vector 2, 3, 4 was here, and as I have explained, vector 2, 3, 4 simply means that you scale the unit vector twice, you scale the y vector as in the j vector 3 times, you scale the z vector 4 times, and you do a summation of all of it. As in you scale the x unit vector I 2 times at the tip of it, you move scale the 3 times j, and then you again move out 4 of z. And the place that you have reached is your vector. Now somehow I have to rotate it. What should I do? So in mathematics, that rotation is given as a function. And the function is known as the matrix here. So again, just for like your understanding, matrix, although like when you do mathematics, it looks like hey, you just want to uh, add two matrices, or you want to multiply two matrices. But in reality, matrices are the function which is applied to your vector. So let's see, like if I have to rotate this vector from 2, 3, 4 to minus 2, 3, 4, what will happen? So what I will do is the unit vector I will be revolving it around minus 1, 0, 0, because I has moved from the right hand side, it has flipped to minus negative of it. So that's my new unit I vector. That's my the j vector, the unit j vector remains as is, and the z vector remains as is. If I do a matrix dot product with the vector, this is what you get as a solution. And how have you got it? So first of all, just look at the dot product uh, dimensionality. So this is a 3 cross 3 matrix. This vector can be represented as a 3 cross 1 because the number of rows and the number of columns and the number of rows is the same. It means the dot product is possible. And what we will be getting is the rows from here and the columns from here. All right. So what I want you to appreciate here, the fact is matrix multiplied by vector is nothing more than a function of x. This is what you're doing. So in physics, if you do a functions of x, in mathematics, you are doing function, which is the matrix, x, which is the vector, and that's how you get it. Take a pause, think about, hey, if I want to rotate this vector in this direction, which is like the third quadrant, what matrix I should be creating in order to perform this rotation. Again, something very interesting, something a very different way of seeing matrix and the vector multiplication, and what is the exact interpretation of it. So if you just going by that logic, if I had my main matrix here 1 0 0 0 1 0 0 0 1, like which is the by default or the de facto unit I, j and z, if you multiply that by 2 3 4, you will land up somewhere here. So this was more to argue that when you define a vector in the first quadrant, or let's say when you learn about vectors and matrices, it's already in this format. Any rotation that you want to provide to it, as in you are providing a nudge to your vector and the vector is moving, either you do an addition or you apply a function to it. Now the question comes that, hey, if I have multiple matrix multiplication, so you have a matrix 1, matrix 2, and a vector, what does it represent? It represents function of g of x. So this vector gets applied, this matrix 2, which is a function, a g of x gets applied here, whatever is the resulting vector. You again apply it back to your matrix 1. So it goes this way, and then again from here to here. Whatever is the final resultant vector, that is your solution. So all you're doing is you're starting from some vector, you apply a matrix 1, maybe that provides it a bit of a nudge, it moves. Then you again apply a function on top of it, and it moves again. So that's what matrix multiplication is doing to your vector. Just quick one, another important concept, the determinant. So if you have a vector and you want to figure out the determinant to it, so what really happens is you go ahead and say that, determinant has a value. So if there's a matrix, you want to calculate a determinant, what is the value of that? And what is the significance? So like, I don't want to invest a lot of time, but just want you to appreciate what it is doing is it is trying to calculate the area. So if this was the vector 1, this was the vector 2. And when I say vector 1, this was the unit vector 1. In the new world, in the matrix world, this was the unit vector 1. Just like here, this is my unit vector, this is my unit j vector. In the new world, if this is my new unit vector and this is my unit j vector, if I try to apply this function on any given vector, like this particular matrix, which is represented by unit vector v1, the unit j vector v2, if I will apply any vector, if I uh, apply a vector to it, what will be the resultant vector? Will it scale out? Will it scale in? Will it flip? Or will it become zero? What is that? So the determinant is just saying that the value that you get out of it just represents, hey, uh, if it is more than 1, it means that the final vector will be scaling out. If it is less than 0, it means the direction changes. And here is a quick derivation out of it. So all you're doing is you are taking this triangle, which is the total area, and then you are subtracting out the area of this part and the area of this part from the diagram. What's left is the area of this one. This is actually what you are calculating. So if again, I would uh, send a request that you go back, look at the formula of a determinant, which is generally AD minus BC or BC minus AD, depending upon how you have defined your uh, matrix, how it is derived. It is purely derived from taking a complete area and substituting and subtracting out the area which is not needed. And that's how the derivation of a determinant is. And secondly, based on the value of the determinant, it simply speaks about this function is gonna extrapolate, or this function is gonna scale out my vector. This function is gonna scale in, or whatever, squeeze my final vector, or it is gonna flip completely, as in the direction will change. Take a pause and just think about how vectors, matrices, and determinant, they all work in tandem and provide a beautiful abstraction that can be used for the languages now. So given this fact, let's get started. So now what's happening is, again, as I mentioned, that in the large language model, you start with a sentence and you have to predict the next word of it. And as I mentioned, being computers unable to understand character or word, it has to be represented by a number to begin with. So let's say that we have a sentence, white dog was sitting next to a black dog. So first of all, computers don't understand characters or word. So what we have to do is we have to map them onto tokens. So just keep in mind why it is somehow mapped to 23, dog with 12, was with 11, blah, blah, blah. And you see here, again, this dog was mapped back to 12 because both of them are representing the same word. In the large language model, you somehow have to get the vectors, which example, king and queen, somehow together, right? Yeah, ultimately, the aim of the large language model would be the vectors which are similar, somehow they have to be pushed together. So now what we do is we say that, we will represent these tokens. Yeah, and again, folks, I'm providing a very simplistic view of token. It's a bit more, let's say, complex than that. But for your understanding and trying to understand the maths of it, this is good enough. So what happens is every word, we map that as a vector. And here is the beauty of it. So let's say, for example, you have a word. So a word can be whatever. It can be an adjective. It can be a verb. It can be a noun. It can be a pronoun. Certain words can be used in positive sense. Certain words can be used in negative sense. So what I'm trying to say is a word has a lot of context. Just like a human body has multiple features, right? You have a hand, you have a leg, you have mouth, you have organs. So these are the features of a human body. So for a word, there can be multiple features. And the beauty of the vector is every dimension represents a feature of that word. That's why a word can be represented as a vector because all we are saying is each dimension is representing certain facet of the word. We are not claiming which dimension means what. Maybe the dimension x, as in like this point 2, represents it's a proverb. Oh, sorry, it's a noun. This dimension represent, it always comes at the starting of the sentence. This dimension represents, it is always taken on a positive note. So if you look at Chat GPT represents a word, if I'm not wrong, as 768 dimension, the earlier versions of Chat GPT. For this session, what I have done is we have represented each word with 8 dimensions to begin with. So in terms of vector, if white was there, so white would have been represented as whatever vector v uh, is equal to 0.2x, 0.3y, 0.8z, 0.6k plus 0.1l, blah, blah, blah. It means that x was one coordinate, y was the other coordinate, z was the other coordinate, k is the other coordinate, l is the other coordinate system. Just keep in mind, human brain can only think about the 3 dimensions. Any dimension beyond that, like even if you want to visualize, it will be super difficult. Especially if you start doing like fifth, sixth, 7 dimension, it's very difficult for human mind to understand that. But in terms of vector, it's quite possible. So now what is done is you take your sentences, you have mapped that to tokens as in numbers. Each number is represented using certain features, and which is nothing but the vectors here, right? Now let's take at the positioning of it. So white comes at the position 0, dog as 1, was at 2, blah blah blah, and dog again 8 here. So what we do is even the positions are represented as vectors now. So something very interesting, the dog here and the dog at the very end, they are not coming at the same position. That's why if you see the positional vector of the dog at the second place and the positional vector of the dog at the last place is not the same. So what happens end of the day is we go ahead and add the tokens embedding and the position embedding. So this ensures that this specific dog, it's pointing somewhere here, while the last dog is not pointing to the same, it's not pointing at the same place as the previous dog. They are pointing at 2 different places. It means that the abstraction model, the vector abstraction model, is somehow becoming aware if dog comes at the second place or the dog comes at the last place, they will not be pointing to the same position in your 8-dimensional space that we are talking about. Take a moment and think about it. Because end of the day, each of the embeddings here, they are represented at certain positions in the 3D space. Let's go ahead. And now comes the most interesting part, that you take these embeddings, there's a neural network part of it. What it does is it does a forward pass and a backward pass, and using the gradient descent algorithm, it tries to optimize the value of this point 0.3, point 0.8, point 0.6. Like it tries to optimize it, and the whole intent is to start moving the vectors nearer, like the words which are similar. It tries to pushes them together or nearer to each other, so that with a gentle nudge, it can start pointing to the word which is next to it. Because at the end of the day, the LLM have only one functionality: predict the next word. Just take a pause and think about it. So now comes the most interesting part, which most of the folks find it very difficult to understand. That hey, I have got the tokens and embedding for that. I have got the positions. Positions have their own embedding. You add both of them, and just keep in mind the moment you are adding, you are just providing a slight nudge to all the initial word vector, right? Because addition means moving the vector. And because the position of dog in the second place and dog at the last place was not the same, they will be represented as two different vectors in your 8-dimensional space. So now the most interesting part, the query key and value comes. And what is that we are trying to do here? So first of all, we take this embedding. There is a linear neural network which is present. For the sake of simplicity, what we do is we'll assume that the weights, or let's say the vector embeddings that you have here, is exactly the same in query, key, and value. So if you go through the paper, it talks about two operations. You take the query, you take the key transpose, you do a dot product. Whatever is the value, you apply a softmax function, and then again you do a dot product with the value, and somehow magically that represents the whole abstraction or the mathematical model of human language. So we will go into the crux of it to understand why is it happening, and especially what is the significance of value here. So now let's take query into key transpose. So which is this part, you take the query, you take the key, and you do a transpose of it. What it really means. Secondly, whatever the output that you're getting, you try to do a dot product again with the value. What does that mean? So before we delve into the mathematical part of it, I just want you to have a mental model before we proceed ahead from here. So query cross key transpose is nothing but the cosine, as in how uh, close two of my vectors are, and can I attribute that with a value. So cosine similarity has been defined as vector A dot vector B modulo of the Euclidean distance, like, or the length of vector A by B. What is the significance of it? In very simple terms, if the value is closer to 1, it means that both those vectors are very close to each other. That's all it means. So first of all, when you are doing a query comma key transpose, you are trying to do a cosine of it. Example, if I take dog as my reference, these are the different angles or the different cosines or the theta value that you want to derive. Right? So it just provides you a understanding, hey, which two vectors should be close. And because there is a neural network at play, with the gradient descent in place, by calculating the loss function, you are trying to push the vectors or the words which have a similar meaning. Example, king and queen, similar, close to each other. But the interesting part is what is happening with the value now, if when you do this multiplication. And here is where most of the folks don't have an understanding. So I just want you to think, just take this mental model, and very briefly we will go through it in the next part. So attention in the value simply means that first of all, you are scaling the other vectors or the embeddings or the words first of all, and you are doing a sum of it to reach to the final vector. Take a pause and think about it. This is exactly what you are doing, although you end up doing a dot product, but uh, graphically or let's say representation wise, they look so different. In one case, when you do a query comma key transpose, it's a cosine similarity. But when you do the attention value, the output of this, when you try to multiply that with value, you are basically scaling out and scaling in the complete word altogether, the vector embedding of that word altogether, and doing a summation across all of them. And this is a part which most of the folks don't get. And again, it has been blown out of proportion in terms of understanding that how is this happening with uh, the attention value in the attention score into the value uh, matrix. So let's go for a deep dive. So you have your query. Again, I'm just copy pasting. I have copy pasted things from here. So you had your position token plus position embedding that was divided into query, key, and value. So this was my query. This was my keys. What I first of all we have to do is we have to take a transpose here now. So here the number of rows were 9, number of columns were 7. If you take a transpose, the number of rows becomes 7 and the number of column becomes 9. It means that you can do a dot product between these two matrices. Now observe something. Here white dog was sitting next to me was in at the column. Because of the transpose, now it has moved at the top. So when you do a dot product here and here, so what's happening? Let's look at this. So when you do a dot product between your query and the key transpose, look what you are doing. You are taking horizontal row from here, multiplying that with the vertical row here. So white word embedding is being multiplied with the white embedding again here, which is nothing but A dot B. You take two vectors and you do a dot product. And that's why you say that this is a cosine of it. Just keep in mind, we have not done the division, but in the cosine formula, the top part of it, right? This part of it, you are trying to do that multiplication. So in a way, this is cosine similarity. This is exactly not cosine at this point in time. Similarly, let's talk about this one. White with a dog, right? So you take white, you multiply that with dog. And again, I just want to reiterate that 0.3 multiplied by 0.1, 0.3 multiplied by 0.3, addition, sorry, plus 0.8 multiplied by 0.8 here, 0.6 multiplied by 0.7, and you try to take a cumulative sum. So that's how you are getting a cosine similarity. If you look at the paper, they talk about a softmax. For simplicity in Excel, I have taken a weighted average. So first of all, like if you go through the paper, you will realize that they move from, first of all, they get the attention value, and then they have a casual attention. What the casual attention says that you cannot see the future. So it means that if my sentence was white dog was sitting next to a black dog, white will never be able to see dog was sitting next to a black. So that's the reason this all values have been set to 0. This dog sees all the words, right? So there is no 0 here. So what you do is you ensure that the top part of it is all 0. Because while predicting, you want to predict the next word. You are not aware of the next word. That what casual attention means. So first of all, we make everything as 0, and then we do a weighted average. Again, this is softmax. Just for simplicity, I have done a weighted average. So now what you can see here is it says that white word gives 100% attention to white. The word dog gives 44% attention to white and 55% attention to dog. Let's take something like sitting. Sitting says that it gives 27% attention to white, 23% attention to dog. The word sitting provides 26% attention to was blah blah blah. So this was just query comma query dot key transpose doing a softmax, and this is what you get. The interesting part, now you take this particular matrix and you have to do a dot product with a value. And here is all the magic that's happening, that although while doing a query and key product, this dot product resulted in cosine. But when you are doing a dot product between the attention and the value, this is not resulting into a cosine. This is resulting into something else altogether. Although operator wise, you are doing the same operation. So let's look at the interesting part. Let's take white to begin with. So if you have to multiply, if you have to take a dot product, so you have to take horizontally the white embedding, and you have to take the column embedding here. So now what you do is you are multiplying 1 with 0.3, 0 with whatever blah blah blah, and that's how you reach to 0.3. Similarly, if you want to calculate this value, again you horizontally take the white and you multiply that with the second column here. I just want you to take a pause and look at what's happening. So folks, if you can see, this value 1 will always be multiplied by all the values here as you are doing the dot product. Just think about it. Even if I take this particular column, right, you can see here it still takes the horizontal row here multiplies with the column here. And how the multiplication goes? 1 into 0.6, 0 into 0.7, blah, blah, blah. Let's take sitting for an example. If I take this particular row, so sitting, there was an error here. Sorry, folks. Yeah, here, yeah, the dog, right? Again, if you see dog with white, 44% attention. So how will I multiply? I'll take 44 whatever 0.44 multiplied by 0.3. If I move ahead, again I will take 0.55 multiplied by 0.3 here. It means that this particular column, as in the first row, will always be multiplied with white itself. That's what I want you to appreciate. The dog here, this particular value will always be multiplied by this itself. It simply means that you are scaling with dog, you are scaling the white embedding by 0.44. With dog, you are scaling the dog embedding by 0.55. Just take a pause and think about it by going through any of the values here, by any of them. Take a pause, think about it. Although you are doing a dot product, but always the first value, white, white, how much attention should I pay to the white? it always gets multiplied, because what's happening is you are doing a horizontal into vertical and then doing a summation. It means that all the x values, they are getting multiplied by the appropriate scaling factor. So what's happening end of the day is, whenever you do a attention into value, all that's happening is you are first of all taking a sentence. Example, if sitting was the sentence, hey, sitting provides 23% attention, or let's say it scales down dog by 23%. So this was my original vector. You can see here all dog has been scaled down by 23% in context of sitting. White has been scaled down to 27% in context of sitting. Was scaled down to 23% in context of sitting. And then you finally do a add, because you are doing a summation across the columns. So that's what is happening in attention into value. So key takeaways: query comma key transpose results into a cosine similarity representation, while the attention into value results into scaling plus addition. So end of the day, what happens is you start with your embedding, you do the query comma key transpose. What it simply means is, hey, which two words, how similar they are, they have to move too close to each other. And secondly, when you do the transpose part, output value, the attention score into the value, all you are doing is, because of the addition, first of all, you scale down or scale up, and because of the addition, that vector really starts moving towards the word which are close to each other, or grammatically or syntactically, uh, uh, or context-wise, they are similar. They start moving closer to each other. And the neural network ensures that all these parameters that you have, they are trained over time, or let's say they are optimized over time to start pushing the vectors closer to each other. And that's how the mathematical model of uh, the multi-attention head comes into being. Just just a remark, whatever we have described here is a single-headed attention, because we were looking at the whole vector in one go. In multi-headed attention, maybe you will have multiple heads which will look at parts of your embedding. I will post the link of Viswara, which has gone into depth uh, to make you understand the end-to-end building of the LLMs. But this is the mathematical part which was very much needed, which is very much simplified. So don't try to overcomplicate it. This is exactly what's happening. If you have the mental clarity to understand this, this is all LLM is all about. Thank you so much.